Thank you for joining us today. And in this video, we are going to practice using Leibniz Theorem, right? So still on Leibniz Theorem, let's jump right in. Now using Leibniz Theorem, find y prime prime, given that this is equal to this. So here the order is 2. We just want to look at y prime prime, right? So the idea is that we want to use Leibniz Theorem. Most of the times, sometimes you need to look at what the question is asking you for. Maybe if it is objectives, then you need to look at your options before you start working on it, right? So now let's look at what we are going to do and see. Now look at the function. You see that the function is just 1. So we don't know our u, we don't know our what, our v. So here, if we are using the idea of u vin, then I will choose u to be equal to 1 and vin to be equal to the whole function here. But I'll show you the short way where what you can do to work on this. So here I'll start by introducing len so that I can take care of this guy here. So I'll pick len y to be equal to len e m sine inverse of x, and this is the same as len y equals m sine inverse of x times len e, so that this one is going to give us 1. So we are going to have len y is equal to m sine inverse of x. So you see, now this is like in the way of like when I differentiate it, it will be okay for me to differentiate that, right? I think I have video right after limit. We have video coming up on derivatives, so you have you have the idea of how to differentiate each function, invert functions, len functions, as we are coming to do here. So here, when I differentiate this len function here, I'm going to have 1 divided by y times y prime. So that's what I'm going to have. Now the idea is that if I put this one in bracket, for you to differentiate a len function, we said 1 divided by what is inside the bracket times we differentiate what's inside the bracket, which is y here, giving us y prime. Now my m here is constant, so I need to differentiate sine inverse. Now as I said, video is coming up how to differentiate sine inverse. So this is going to give us m times sine inverse is 1 divided by root of 1 minus x squared. So that's what I'm going to get for differentiating sine inverse, right? So this is what I'm going to get. This is y prime divided by y is equal to m divided by root of 1 minus x squared. One thing that I do is I make sure I make my life very simple, right? Try to simplify some things. So I'll do cross multiplication. This multiply this, this multiply that. So we are going to have root of 1 minus x squared times y prime is equal to my. Now because of this radical here, root here, differentiating this will be so complicated. So the best thing for me to do is to square both sides, right? Then I just go. But don't forget, we are dealing with Leibniz. So instead of the prime, let me make it down there. Yeah. So I'm going to square this. I'm going to square this and also square this so that I can take care of the root here. So this will cancel this and square this one too. So I'm going to have 1 minus x squared times y1 squared. So if I have a product to a times b squared, this is the same as a squared times b squared. So I will square this, which this will cancel this. Then I need to square this one too as well. So that's what I'm going to have. and then this side will be m squared y squared. So you can see that now we are done with the first derivative. The question was asking us to find this, right? The y prime prime. So we need to differentiate it again because this is the first derivative. So we are going to have, so this right here is a product rule. So I maintain 1 minus x squared. I maintain 1 minus x squared. Then I differentiate this. When I'm differentiating this, I'm going to have 2 y prime prime, which is going to be 2. So this that I have here is like I have y prime squared, right? So I want to differentiate it. So I'm using the power rule. These two will drop down and subtract 1. So I'm going to have 2 down y prime. When I subtract 1, it will left with 1 times. Then I will differentiate what's inside the bracket. What's inside the bracket is already differentiated once. So when I differentiate it again, it becomes y prime prime. But with Leibniz, this can be written as, this is 1, right? So we just 1. The y prime can be written as y1 and y prime prime can be written as y2. So that's the reason why we are having this one right here. Then plus, now first I maintain this and I differentiated this. Now I need to maintain this and differentiate this. So I maintain y1 squared and I differentiate what is inside the bracket here. I'm going to have negative 2x, which is equal to, the m here is constant, so I'll just differentiate this, which is going to give us m squared. Let me try and clean this one. So this one is going to give us m squared. When I differentiate y squared, I'm going to have 2y y1. So it's like I'm differentiating y squared. So this is like 2y y prime. But as we said, y prime can be written as y1. So that's the reason why we are having this one also here. Okay. So now that we have this, then let's try and simplify and see. So now I can see that I have y1 here, y1 here, y1 here. So I can decide to divide through by y1, divide through by y1, divide through by y1. So this one will cancel this one will cancel this, and one of this will cancel this because this one, the y1 is 2 times. So I'm going to have, when I divide through by y1, I'm going to have 1 minus y squared times 2y2 plus this one. When I differentiate, when I divide it by y1, it will be left with just 1. So I'm going to have minus 2x y1, which is equal to m squared. So let me bring the 2 first. 2m squared y. So this is what I'm going to have. And finally, I can decide to rewrite this one as 1 minus x squared 2. I'm bringing the 2 in front. So 2y2 minus 2xy1 minus 2m squared y, which is equal to 0. So this is the second derivative in terms of Leibniz rule. And you see, we can even go ahead from here. If we ask you to find the nth derivative, then here you need to go ahead and go and differentiate again. So here we can apply the Leibniz theorem by saying that if I pick the first one, my u will be equal to 2, 1 minus x squared, and my v will be equal to y2. When I pick the second one, my u will be equal to negative 2x, and my v will be equal to y1. And when I pick the last one, my u will be equal to minus 2m squared, and my v will be equal to y. Then I need to follow the procedure. But I'll do something for you to see. And now, if I want to differentiate this, remember that this one here is already differentiated 2 times. So what will be y1? y1 is going to be sorry, Vn1 is going to be, this one is differentiated 2 times. So when I differentiate it again, it's going to be what? 3 times, right? So when I differentiate again, it's going to be 3 times. So this one will be y3. y2 will be y4. y3 will be, sorry, y2 will be y4 and y3 will be y5. But I want to write the Vn. So how can I do that? Now I'll start from here. I want to make sure that I have the 1 here. So 3 can be written as y1 plus 2. This one can be written as y2 plus 2. This one too can be written as y3 plus 2. So that what I'm doing is I'm trying to make sure I have the 1 here, 2 here, 2 here, 3 here, 3 here. And because of that, I can see that I have 2, 2, 2, which is constant throughout. So if I have 1 and 1 here plus 2, 2 here and 2 here plus 2, 3 here and 3 here plus 2, then my Vn will be yn plus 2. So that I'll have n here plus 2. Sorry, it's supposed to be yn plus 2. So Vn n here n plus 2, 3 here 3 plus 2, 2 here 2 plus 2, 1 here 1 plus 1. So that is how you can differentiate functions like this. Is that right? Yeah. So this is how we are going to go through the process. Now try this, the same process. You see that this is sine inverse, but I just change this one to cos inverse, and then I have m here, and this should be your results when you do it. This should be your results. So you can try this one and compare your final results with this. See you in the next video.